Now, there are many types of inequality in this world. There's racial inequality, there's gender inequality, but today I want to talk to you about a type of inequality that is very near and dear to my heart, and that is the arithmetic mean geometric mean inequality, perhaps better known as the AMGM inequality. What is the AMGM inequality, you might be asking? Well, let's start with its statement. The AMGM inequality says that the average of two numbers, otherwise known as the arithmetic mean, is greater than or equal to the geometric mean of two numbers. So let's look at an example at why this might be true. If we take x is equal to 3 and y is equal to 27, then we will see that the arithmetic mean of x and y is simply equal to 3 plus 27 over 2, which is just 15. And that should be greater than or equal to the square root of this guy, which happens to be the square root of 81, which is 9. So that is true. So that's a piece of numerical evidence. Obviously, that's not a proof. We'll get to that later. But hopefully, it should be a little bit convincing. Now, when I told you that this was the arithmetic mean, geometric mean inequality, I actually lied. So this is the arithmetic mean, geometric mean inequality for two variables. But actually, in fact, the AMGM inequality has a version for any number of variables. So you could have an x and a y, and you could have a z as well, or you could have 4 variables, or even more. So let's state the general version of this inequality. That turns out to be written like this. So the sum of x1 plus x2 plus ... plus xn over n, again, you should recognize this as just the arithmetic mean or regular average. This is actually greater than or equal to the nth root of x1 times x2 times ... times xn. And you should recognize this from our previous video as the geometric mean. And you can see how if you set n is equal to 2, then this inequality is really just the same as the one we wrote down before. Now let's work through an example with a different amount of variables. So let's say we have x1 is equal to 4, x2 is equal to 5, and let's do just one more. Maybe x3 is equal to 50. What would the AMGM inequality look like in this scenario? Well, let's compute. The arithmetic mean of 4, 5, and 50 is 59 over 3, which is just less than 20. And the geometric mean, on the other hand, is equal to the cube root of 4 times 5 times 50. What is that? That is simply the cube root of 20 times 50, which is the cube root of 1000, which is equal to 10. And recall this was almost 20, so this is certainly greater than 10. Now in both of these examples, it actually turned out that the arithmetic mean was greater than the geometric mean, not just greater than or equal to, but greater. However, there are plenty of examples where the two sides can't be equal. So I'll leave it to you to pause the video and think of an instance where they might be equal. And here's a hint. It might be somewhat of an easy example. Okay, if you're still with us, then I'll assume you've tried out on your own. And one instance, for example, is if you have all the numbers equal. So say you had, let's go back to the two variable case. So you had x is equal to 2 and y is equal to 2. Well, then you would have 2 plus 2 over 2 is greater than or equal to the square root of 2 times 2. And in this case, both sides are equal to 2. So you do have equality. And in fact, you have inequality, or you have equality if and only if all the numbers are equal. So if and only if x1 is equal to x2 is equal to ... is equal to xn in the general case, or if x is equal to y in the two variable case. So finally, to leave off this video, I want to leave this as an exercise for you guys. So I want you guys to prove this equation. Hopefully it shouldn't be too hard, and if you get stuck, I'll leave a hint in the description for you. Alright, good luck, and we'll go over the solution in the next video.